Hello, you brilliant in training physics kids. We're going to be going over Mechanics 12 and 13 today. So if you have them out, it would be good to look at them. This is all about wedge problems. Now, the reason that I personally love teaching wedge problems at this point in physics, because it basically reviews all of the physics we've gone over so far. If you can understand how to do the physics we've done so far, wedge problems are the way to show it. If you're a little uncertain here and there, wedge problems will often help you fix whatever you're having trouble with. So wedge problems are pretty cool. So we're going to start out with the easy one, which would be a frictionless wedge problem. And all a wedge problem is an inclined plane. Planes are usually flat. This one is tilted on its side. So we need to break the acceleration due to gravity into different components based on the angles. So let's get into it, and I think it'll explain itself. So we have a wedge. I'll just draw one. We've got a lovely wedge there. All right, so the information that you might have looking at this, I'm going to suggest maybe 36 degrees down there. 36 degrees, that's an important measurement. And what about a mass sitting on it of 3 kilograms? Okay, so the question is always, with a wedge, the question is always going to be, what is the acceleration down that plane? Now, you know it's not going to be 9.8 meters per second squared, and if you're unsure about that, take it to the limit where the inclined plane is tipped ever so slightly. You're not like screaming, falling at 9.8 meters per second squared like you would be if you were just, whoa! No, this is a tiny component of that accelerating you. So we're going to use our awareness of vectors to work this out. All right, so we have this going straight down. That's going to be the object's weight. Now we can calculate that pretty easily, can't we? Right? 3 kilograms times 9.8 meters per second squared. We're doing calculations, so don't use 10 meters per second squared here. So 3 times 9.8 meters per second squared gives us 29.4 newtons. So the weight right away is 29.4 newtons. Great. Well, how do we use the angle here? Check this out. This is really cool. We know the angles of the interior angles of a triangle. Remember what they add up to be? 180 degrees, right? So this is 36 of them. Because this comes straight down and meets the bottom, perpendicular to it, that's 90 degrees, meaning that this angle here, I'm not even going to bother calculating it. It's the complement of this angle, right? In other words, this plus this make up 90 degrees. That's the other 90 degrees. Okay, check it out. Well, we're going to break this vector up into 2 additional vectors that together will add up to it. Right? We're doing sort of like adding our x, y vectors, make our hypotenuse, same exact thing. But the first vector we're interested in is the vector going perpendicular into the inclined plane. Got that? That would be the perpendicular vector. And we would call it, if this is the force we would know as the weight, this would be the force. We're not going to get poetic here. This is the force we'd call the perpendicular force. All right. What do you suppose we're going to call this force that is exactly parallel to the inclined plane? Exactly parallel. What do you suppose we're going to call this force? Bet you got it. Parallel force. Okay, so can we break them up? Well, we need an angle, don't we? We need an angle in this triangle. Check it out. 36, this is the complement of 36, but this whole angle here, this going to the perpendicular line, that's 90 degrees. So if this is the complement of 36 degrees, what do you suppose that is? 36 degrees. So now we have everything we need. We have the hypotenuse, 29.4. We have the interior angle, 36 degrees. Now I can find my force parallel. I could find my force perpendicular. For this wedge, I don't need my force perpendicular, because my force perpendicular isn't doing anything if it's a frictionless plane. So the first case we're doing is frictionless. The only time we're going to do frictionless, but just to give you an idea of how we do it. So all we need to do is calculate force parallel. Well, how do we do that? Here's an angle. This is the opposite side of the angle. That's the hypotenuse. This must be, by the way, this must be a right angle between perpendicular and parallel. Does that make sense? They would meet at a right angle. So this is the opposite side from 36. That's the hypotenuse. So what would we use? Correct. Sine of 36 degrees equals, well, let's see, SOH. Good. Sine equals opposite. That's force parallel over the hypotenuse, which is 29.4 newtons. See it? Okay, so what do we get? From the calculator, you enter. Oh, I'm sorry, we need to solve. So force parallel is sine of 36 degrees times 29.4 newtons. Okay? You see that over there? I think you can. All right? So, enter 36, press sine, times 29.4. That equals 17.3. So down here, we have F parallel equals 17.3 newtons. Well, remember the free body diagram? Where would I attach that? Right to my block. Pulling it down, 17.3 newtons. And if that is the only force, because we don't have friction to resolve, that's the only force. If that's the only force, how do I do it now? Well, how about F equals mass times acceleration? Acceleration is, how do we solve that? Right? Divide both sides by F. F over M. Or 17.3 newtons divided by 3 kilograms. Newtons changes to kilogram meters per second squared, canceling kilograms, giving me my acceleration. So if I divide this by 3 kilograms, 5.8 meters per second squared. 5.8 meters per second squared. So that's how you do that. That's all there is to it. All right? We take the mass, we turn it into a weight. The weight is pointing straight down. We break another vector perpendicular to the inclined plane, bring that down. Then we have another vector exactly parallel to the inclined plane. Right now, it's this vector that we care about. So we solve this triangle for this value. We find the force that's pulling this down along the inclined plane. That force, there's nothing to pull against it. That's going to be the next problem when we introduce friction to this. But right now, that's the only force acting on that mass. A equals F over M. We end up with 5.8 meters per second squared. It goes over basically all the physics we've used all year long. It's a great workout. The next one is mechanics number 13. That's where we introduce friction to this. And it's just one more element into how to do it. Places where we screw this problem up, very often right here, when we do the drawing. If you draw this backwards, this doesn't work. Always remember, the weight must be pointing exactly straight down. That's how weight works. And if weight is pointing exactly straight down, you're probably going to do this okay. Remember, weight is going to be the biggest part of this triangle. It's got to be, because the other forces are components of that weight. So if we draw this perpendicular, we draw this parallel, we got it. Hard one to miss if you do the drawing correctly. So pay very close attention to the drawing. Got it? Well, we'll do some more for you. Thanks for watching.